I've been using live programming and interactive visualizations to help students come to grips with concepts that might be difficult for them to grasp via either static diagrams or equations. So this is what a typical lecture slide looks like in the physical sciences. There's a diagram, there are some equations, and they're both static. I want to bring this slide to life. Modern physics is more about seeing patterns between the physical universe and mathematics than it is about performing cumbersome mathematical evaluations such as this. Yet we still predominantly teach the practice of physics as one of performing these cumbersome mathematical evaluations by hand. And this is quite divorced from the practice of the modern physicist, like us, who reaches for a supercomputer over a slide rule. So we want students to be aware of these tools and use them themselves for things like simulation and visualization. So what tools do we have at our disposal? Well, there are a limited set of canned simulations on the web, and while these can take students closer to understanding something, they take them no closer to them doing their own simulations. So we want students to code, and this has been recognised nationally at primary and secondary STEM. The Department of Industry have released this competitiveness agenda. In it, they outline some $12 million of initiatives, such as the Coding Across the Curriculum program. But this preparedness for the data science workplace is in vain if we pretend as though computers don't exist in undergraduate science. That's not entirely fair. There are some dedicated scientific computing units, but they give the students this impression that scientific computing is distinct from the rest of the syllabus. So this is something we've been working on at second year physics, where we have scientific computing classes in every single unit now, and Tim will talk about that next. Here's an example of a live visualization that I write during lectures. It's of a laser beam. And I write the simulation from a blank Mathematica notebook from scratch, and in a few lines of code, and not much work at all, just a few lines of mathematics, I get an interactive visualization of this laser beam, and it provides a teachable moment for something that I can be heard saying during the lecture recording. And now I really just have got this equation and turned it into a graphical machine with a dial. There are two things I want students to take from this. One is that without much work, just a few lines of code and one or two equations, they can write such a simulation for themselves. And the other thing is that equations are just machines with dials, and with very little effort, they can turn those dials to see how the physical universe works. I understand that most of you don't play with laser beams all day, so I want to provide an example that hopefully everyone can enjoy of a live programming demonstration. I don't expect you to follow along with the code, but I do expect you to follow along with the joke. So a farmer has a set of cows that he is trying to milk. Sorry, Peter. And the milk is not coming very fast. So he contacts his local university, and he enlists the help of a psychologist, a pharmacologist, and a physicist. They go away for 2 weeks and have some intensive investigation, and after a couple of weeks they haven't reached a consensus. So they come back to the farmer and tell them their results individually. The psychologist says, happy cows produce more milk. Paint your milking stalls green. It will remind the cows of their greener pastures, and you'll have more milk. Good. The pharmacologist says, administer a pituitary hormone such as somatotropin. This will increase lactation. Fair enough. The physicist comes to the farmer and he says, aha, I have the solution. But it only works for a spherical cow in a vacuum. And here is that spherical cow in a vacuum. Yes, Peter.
Do all the students have access to Mathematica?
Yes.
It's on the web. It's on the cloud now. It's not. I can do it on my phone.
To bridge the divide between me doing live programming in lectures and students writing their own simulations in workshops, I developed a series of online interactive visualizations shown here in the Moodle page for these two units. This is where the students go to get their daily dose of content, and it's a great place to put such an interactive visualization. Here's another one in 3 dimensions. This is an example of electromagnetic radiation, or light, propagating in 3D. You can choose different types of polarization states from the left-hand side here. And because it's an animation, we can play it and pan and zoom it around. It gives a hands-on feel for the visualization. I found that by making these interactive visualizations relevant to assessments, it greatly increased the participation with these tools. Moodle Analytics revealed a 2.5 times increase in participation once making them relevant to assessment. So I want to take the last few minutes to wax lyrical about what I think makes effective visualizations. I'll break it down into 3 rules. The first is keep it simple. The second is roll your own, or DIY trying. And the third is do it live. So let's take a look at these in a bit more detail. Well, the first one's simple. It means less work for you, and that means that you'll make more content. The second one, roll your own. This is really important. It takes away the sense that these simulations are a black box, and it's a good example where seeing how the sausages are made is actually a very good thing. And this demystifies the process of writing simulations, and that is empowering for students, I've found. It also shows students how you come to understand things, or certainly how I come to understand things, is by writing code and doing simulations. And if they see this process, it will inspire them to undertake it themselves. This doesn't always have to be contrived either. An example for me that was recent that wasn't contrived is when I posed a question to students: why is a soap bubble not a rainbow? They're not the same thing. This is a great example of why a soap bubble isn't a rainbow. The colours are different. And for a couple of years, I've written a toy model in lectures where I basically take thin film interference, find out what wavelength is transmitted for a given film thickness, and I get a pretty basic reproduction of this phenomenon. I have the colours going from blue through to purple and back to blue again. But it's very limited. All I've done really is simulate a rainbow. So, inspired by my students last semester, I went on a deep dive into a field called Colorimetry, which connects the physical generation, the human perception, and the graphical display of colours. Doing so, I was able to produce these colour gradients like this, colour here as a function of some film thickness for a given reflectivity, and make pictures of soap bubbles, exactly as they see in nature. And just like anything you've come to understand recently, for a while thereafter, it's all that you can see. And this was certainly the case for me when I was getting on the train one morning. Check this out. That was their response, and being a dork in front of your students is highly recommended. Another example that happened before class one day was the second presidential debate. And I was watching it on YouTube live, and I saw this great thin film interference in the glass cover slide of the camera. And this colour gradient here should be very familiar to you. In fact, overlaying that colour gradient directly onto this image, we see remarkable agreement. There's been no scaling here other than just a linear stretch, and it's exactly the same colour gradient you see everywhere in the world. Because it's got the connotation of the US presidential debate, it does make you wonder whether there's something more nefarious going on as well. The final rule is do it live. I ask my students before starting a semester, why would you stay at home and watch the concert on DVD when you've got tickets to the live show? I really do think there's a great nexus between teaching and performance, and this is the real kind of question that we have to ask ourselves. This then does oblige me to give a performance akin to a rock concert, hopefully with a little less makeup.
Oh, come on. Bring it on.
But students want to know the answer to this question too. And I think that there's an atmosphere we can offer them that they don't get at home. This atmosphere derives from things like storytelling, suspense, and a sense of unpredictability. Finally, people are afraid of performing something live, even if it's a practice they are masters of. Don't worry about it. Fail and fail again. Failing provides an authentic opportunity to show students how you come to grips with making a mistake. I know that troubleshooting even simple arithmetic errors can be extremely hard in front of a theatre full of people, but after a bit of practice, it's well worth the effort. Here's a sample of what the student said. And here's what Agent Smith said.
Why, Mr. Anderson? Why? Why? Why do you do it?
Because I want Monash students to see the matrix and not just see the matrix. Thanks.